All right, folks, back here with what I hope is a quick little Mathematica demo for you. As I had promised, I was going to put together. We'll try to give you some way of doing a analysis of a vector valued function using Mathematica, right? Just to take some of the sketchiness out of the process and give you something with a little bit more accuracy, because when we start to look at this, that's what's going to help with our understanding, is having some of that understanding of accuracy. So I did present to you back in the first set of notes a couple of problems here where we look at an analysis. We're going to look at everything but the domain. The domain is really just a question of what is an acceptable input for the independent variable, right? And we have a couple of concerns for domain, one of which is underneath an even radical. That t plus 5 always must be greater than or equal to 0. So in this case, our domain t is going to have to be greater than or equal to negative 5. Sine and cosines present no case for domain concern, neither does a linear function. I don't know about our third example. Did we have any domain concerns down here? No, we didn't have any domain concerns down here either. But other things you want to watch out for are what? T's and denominators, or parameters and denominators, will cause concern. And logarithms, arguments inside logarithms have to be greater than 0. T's and denominators cannot equal 0, right, in our study of math and study of algebra. So those are our domain concerns. What we might look at doing, though, is using our Mathematica to help us make tables. And we might consider using Mathematica to help us make these graphs. And then even I got a quick little line of code that I can give you that might help us determine the corresponding rectangular equation a little bit more easily, right? Or at least kind of give you the equation in a functional context if we see nice functional behavior. And actually, it might not, it works. It works some of the time. We'll put it that way, right? How often? Well, that's really a question of how complex, right? So we'll see what we get into here with a little bit of the analysis we're looking at. So and I do see a couple areas where it would be a bit buggy. So, but I'll see if I can explain along the way, at least with an example in terms of how to find that rectangular equation. So I do present these first three examples here. Let's see if we can do a little bit of analysis with these over in Mathematica, right? So what I do have here is the Mathematica window open. What we are going to be working with are functions in Mathematica. Let me see how clear that is. That is pretty clear. And just to begin with, to highlight my input cells, I am going to, while highlighted inside that input cell, hit Alt-8. If I do Alt-8, you will see that, oh, hold on, I got to flip over. I thought I flipped over. Here we are, over in Mathematica, right? I was just putting in a bit of input here, right? I can actually go back in and just, remember, you can delete out an entire cell. There is my input cursor waiting to go in Mathematica. And I'm going to put in a function, right? Let's start off with just a little bit of functions on Mathematica to help you recall if you haven't watched the video on the other demo yet. I haven't done it yet, but you may have stumbled upon this after the fact. So if we just go a little bit over functions here, to put a function into Mathematica, there's a unique set of notation. We can declare our own functions, our own operations. And let's say we wanted to put the notation in there for function f of x equals x squared. Well, we could certainly just start to type that, f of x. Now, in Mathematica, the declaration of functions is going to require the use of brackets. They are going to act as wrappers. Here we're going to have this wrapper function f, where this wrapper takes as input this quantity x and gives as output the dependent value f of x. And we can either use and then the other thing we point out is that when we apply that wrapper here, when we go to declare an actual function ourselves, we inside that function notation, inside that parentheses, to highlight the independent variable, we state the variable we're going to use, and here we're going to just go with scalar value function for the moment, talk about f of x. So we highlight x as our independent variable, and then to help highlight that independent variable and have Mathematica recognize it as an independent variable, we're going to put an underscore. We do follow that with shift minus and put an underscore after that value of f of x. And I could declare f of x as a function maybe of just simply x squared. Right? That would be the square function. And when I hit shift enter and return that, that's exactly what Mathematica will tell me, is you just assigned f of x the value x squared. We declared it to be that value. Now, you could also go back and just set declare it using a colon. That will set declare it, and that will kind of hold it in the background, waiting for that value to be called upon again. So if I was to come along and say, also in my code, f of x, right, it would then declare, well, yeah, f of x is x squared, right, based upon the line of code above. And another thing I like to do in Mathematica is actually highlight this line of code. And I do that by actually just clicking into the cell and hitting Alt-8. And you will see that that does take that cell over into the coding, what we might say, coding format for Mathematica input. And this kind of highlights the entire cell and kind of says this whole thing acts as a group, almost like a line of code here. So this is just saying, declaring f of x and then saying, well, what is f of x? I could also come along and say, well, what is f of x at -5? And I could inquire on that value, and I could find that as 25. Or I could say, what is f of x at the quantity y plus 8? Right? Well, that's a plus y squared. Or, I should be careful there. Let's put that back in the line of code up here. So you can't copy and paste lines of code over. Let's get rid of this. I want to try to keep everything together. Right? We could even come along and say, let's expand that, right? And we can expand that out into its quadratic form if we also desired. Now, what we like to do with functions, we like to make them into tables. So I could make a table here of f of x values that start at a value of x and run from 0. Well, let's go negative. Let's go -5 to 5, right? And I could make my table of values where there I'm just repeating the value f of x. I could actually organize those into groups with x by making this a bit more of a group out in front here. And the way that we kind of approach this group or coordinates or, sets is how Mathematica looks at things. So we look at this as a table built by a set of values given by x, the independent value, and f of x, the dependent. We could also do that. And look at here, preparing this grander set of those corresponding values in that relationship. Now, we do like to see our tables organized vertically, so we could come along and make that into a column also, right? And see that kind of organized into a bit of a column if we wanted, right? Now, Mathematica will then also allow us to graph this function. We could come down below here and we could make a plot of f of x, right? And do that over values of x from 0. Well, let's do -5 to 5 again here, right? And we can build, right, this as a corresponding output. All right, let's go back and if we use a semicolon after that table, it will just delete that table. And actually, let's get rid of these lines of code. Let's go into the more interesting plot and column tabling here. So notice I turned off the column for the meantime. I could turn it back on. All right, we can see that a little better in our illustration here. And actually, let's get rid of the column aspect of it. That's just another way to keep this nice and horizontally organized. Right, so there is our table of values. There is our plot. Some other quick things just to make note of with these functions. We could also come along and make a list plot of values. Right, that list plot could be made up of our tabled values. I could come along and call my tabled values T1. Right, I'll say T1 equals this table, And I could come down here and make a list plot of these tabled values. And you can see there it plots it out in space. I have essentially a plotting of that table of values. And then what you might really want to do is actually put these two plots or graphs on top of each other. And what we could do to do that is we could call this maybe plot 1. Right? We could call this plot 2. And that's what the show command is. I could come along and apply the show operator to plot 1 and plot 2. Now, where is that? That's down below here. I could scroll down, and here's plot 1 and plot 2 combined. I could actually go in and set declare these so it doesn't spit out all this data each and every time, all this information, and just give me the show at the end. And there's the show at the end. There is the graph of this relationship, this function, and we can maybe bring the table back into view. And then there is that plotting of those few plots we might see on that table. If we want to add maybe some more plots to this graph, let's do increments of, here it's incrementing by 1, let's actually do increments of a quarter, 0.25, right? It'll do that plotting, and it'll repeat everything to us in terms of decimals, because that's what we put it in there as. It's saying, all right, you want decimals, huh? Or we can do by a quarters, and it'll do it by quarters also, right? So we can make our plots that much more intricate if we would like, just working with functions. All right? So that's just the beginning here. What we might consider now doing this is for vector valued functions, doing something very similar. If we were to do something similar for vector valued functions, let's maybe start another window or another code here in our program, right? Let me now actually what I want to maybe do, we maybe want to, let's go back and do this for our first case back here in our examples. Let's do that for this vector valued function seen here, that vector valued function t plus 3 square root of t plus 5. I think I can remember that. If we flip back over to the Mathematica here, the way that we are going to input a vector valued function into Mathematica is similar to scalar valued function. We are going to use the notation r with the brackets. Now, there is no way to put the bar over top of r. What Mathematica is going to recognize this as a vector valued function, not because of the notation we have on the left-hand side, but how we're going to denote the function on the right. And the way we're going to denote this function on the right is we are actually going to wrap the, well, we're going to express it as a vector whose components are wrapped with the braces symbols, right? And this is going to be a function of parameter t, so we will put the t over in the brackets with an underscore. And let me make this just a little bigger so we can all see that, right? Clearly enough. And over here, we'll go ahead and declare that function. Now, I do think it was t plus 3, comma, and in Mathematica, we can use the sqrt for square root. That is an operation that's going to be performed here on t plus 5 in value. Now, what that does is that does declare r bar of t. If we were to hit enter there, you could see certainly Mathematica would define it as a set with two components. The first component being your x description of displacement in terms of t, your second component being your y component of displacement in terms of t. Right? And we could certainly come along and consider evaluating r bar at certain values. Maybe we want to evaluate it at the value of 0. Right? We could certainly evaluate it at 0. That would be 3 square root of 5. Right? We could evaluate it at other values of some variable, some parameter. Maybe we want to evaluate it at r bar of s plus 6, right? And we can certainly evaluate it at r bar of s plus 6. And notice it did a little of the quick simplification along the way, right? Now, what are we interested in? We're probably more interested in the tables and the graphs. So let's go back here, and instead of just looking at individual values, let's look at a table of values. Now, again, just like earlier, we're going to make a table of r bar of t values that are going to occur for values of t Now, what was our lowest domain value? What was that? That was negative 5 in value, and let's have it continue up through maybe 5 in value, right? And we know if we don't follow this with any incremental value, it'll automatically default to an incremental 1. But if we did want it to increment by something other than 1, we could follow that those bounds on our tabled values with an incrementation, right? Here by 1/2 if we wanted. It does it by default by the value of 1, so if we leave it blank, it will go up by 1 unit, right? We can see that in this table of values. Now, you'll notice it is just giving us the values of r bar of t over those values of t. It is actually not reporting the value of t itself. How to actually get it to report the value of t itself that's causing all of these dependent values. This is strictly the listing of dependent values. We could actually make a table for a set of values made up of our independent variable r t and our dependent value r of t, right? R bar of t. So there we can make that table, and actually that might look a little nicer to us just for the moment. Let's go over and put that into a column for the moment, right? We can see that as a nice column of values. These are our t values, right? These are our t values. These are our r bar of t values. Remember, the vector valued function takes as input a scalar value of a parameter, right? This parameter t just exists off in its own one-dimensional space. But what we get back is a dependent value in the two-dimensional case. The fact that we're dealing with a two-dimensional vector up here is a two-dimensional vector description of position. At each of these points in time, we see this particular position. All right? Now, how do we make a graph of this? Let me take it out of the column form just to keep it nice and cleaner, right? And in fact, we might turn that column or that table off for just the moment. And actually, we don't want r bar of t to always report to us, so I could actually set declare that. And we would be just fine. So I'll set that to set declare. Right? And now you can see we don't get much because I've turned off the table and I have set declared r bar of t, waiting for its call up. And what we're going to do here is consider plotting r bar of t. To plot a vector value function in two-dimensional space, we're going to use a parametric plot. Right? That will be how we graph these in a two-dimensional space. In a three-dimensional space, we would do a parametric plot 3D. And there's a small difference between the two. One of them will be that you're dealing with a three-dimensional vector versus a two. Well, that would be your only difference, is that you're dealing with a three-dimensional vector versus a two-dimensional vector, right? So we're going to be making a parametric plot here in two-dimensional space of vector r bar of t, and we're going to be making it over values of t from, let's go with our lowest domain value at -5 and then continue up through that value of 5 there. And you can see we make that plot scene here. And certainly we can consider adding some consistent ratio here just to keep it in a nice illustration. Actually, we might make it a little smaller to fit on the screen with everything. That's image size. Let's make it image size 200. Might get it to fit rather nice in the screen here. All right. And then let's axis label this, just to make sure we're clear on axis. Axis label. All right. And notice these commands are also similar to what you could put above for just any old plot. These are generic plotting commands. I'm going to label the x-axis x equal to x of t. And I'm going to label my y-axis y equal to y of t. And I am wrapping those statements x equal to x of t and y equal to y of t in quotation marks, which makes Mathematica recognize them as text, right, in their label. And we can see there we get a nice little label on that graph. All right, so this is a visualization of that vector valued function. Now we can maybe fancy this up a little bit. For instance, we could potentially put those tabled values into this graph again. We could Let's come over here and, as we did last time, call this maybe out as table 1. All right. I'm going to go ahead and set declare that because I don't want table 1 to repeat out to me. And we can make a list plot of table 1 values. And actually, what we are going to have to put into table 1 here is we don't want to include the t. Let's just go back to what we originally had and just those r of t values. And that will make a list plot. We can see those plottings seen there. Let's actually call this plot 1. Let's call this plot 0, folks. Let's call that the base plot. And you can call these anything you want. You can call this table whatever name you want on the left-hand side. I'm just calling them P1, P0 just to help keep track of it all. And the reason I do that is because in the show command, whatever plot you put first will be the plot that dictates how all the plot options happen. And since I'm stacking up my plot options here in P0, these plot options seen here, I want those to kind of roll over into the show of both of them together. So I'm going to put that one first. I'll put that as my base plot. And I get this nice illustration here. Right? If you don't like the point sizes on that plot, right, those we can maybe make those points a little bigger. I do think we can go in here and say plot style. And we could go in and call the point size a little different. We can say point size. Let's go with, I hate to call something too large, but let's just see what happens. What if I go 0.4? Those are really big. All right. It's based upon scale, folks. So maybe we do a 10% scale. See, that's really still quite large. So maybe we go a 5% scale. Right, so they get a little smaller. Maybe a 0.025% or 2.5% scale. And see what they start to show up a little nicer. And in fact, in plot style is where you can call out color. If I want to put several plot styles in at one time, I do have to use the directive command. So I'm going to use the directive command here and wrap up my directive commands with a little color. So let's make, I like magenta. Magenta is always nice and flashy. Right? So I can put those points nice and magenta colored on my graph seen there. Right? So those are the table values being plotted out in this on this curve. Right? On its vector value description of a curve here. Right? Let's see here. One thing that might be lacking here is a little orientation. What is forward orientation on this curve? To actually get the orientation indicated the way we want it here with a bit of an arrow, we are going to make use of a graphics in Mathematica. We are going to make use of an arrow graphic, right? That is going to be in the shape of what we call a Bezier curve, right? The Bezier curve is a connect the dot curve. Well, arrows behave like connect the dots, where I could put in here a set of points. I could put in just the table points if I wanted to. Table 1 points if I wanted to. And the arrow graphic would play connect the dots with those. But you can see it doesn't make a very smooth curve in my picture. To smooth out this curve, we can make a Bezier curve, which is also going to play the game of connect the dots with the arrows. But the way that it plays it is as it goes from dot to dot to dot, it tries to make the smoothest curved transition through those dots. And we could make this on table 1. And you can see there it does smooth it a little bit more cleanly as a graph. But we could even make that a little bit nicer, a little bit smoother in its illustration by including more points in its table. So what I'm actually going to do here is I'm going to make another table. Right? Let's leave the table 1 alone and let that highlight those magenta dots in our graph, the magenta points. And let's go in here and declare table 2 to also plot r bar of t on this interval from -5 to 5. And let's actually have that increment by a little more than just every unit. Let's maybe go by 1/10 of a unit. All right, let's go by 1/10. And you can see that curve certainly smooths out a little bit more. And I think we could even go up to a, whoa, you know what I didn't do? I didn't put the curve down there, so I'm lying to you. That's not the curve. Here's the curve. You can see that curve smoothed out a little more. But let's do this even further. Let's go out to 100th maybe. Mathematica is pretty powerful in the background there. It's not suffering too much. Right? And what I'm able to do now with this is I can actually come over and drop, as with the plots, I can organize these all into one show command. So I'll call that graphic 1, G1, and I'll bring it over into the show command. And you can see here it's placed these all into a single illustration of this curve, right? And this the way this arrow is behaving. And certainly you can, if you want to, how to call out a graphical value, a color, you have to make it a set and then call it a color. Let's say we want to make this arrow green, right? I could certainly do that and get a nice green arrow in this picture. If I wanted to control where the arrow began or stopped, if I only wanted to go halfway through the cycle, I would do that up here in the table, right? And I can have that portion of the orientation here, right, going from 0 just up to, well, from -5 up to 0 here in my cycle. All right, folks. This is just a little quick analysis here. And we can actually turn this into a little bit more of a powerful program if we wanted to handle two-dimensional two-dimensional vector analysis and be able to approach this with really many different types of two-dimensional vectors. If I was to adjust just some aspects like this lower and upper bound, if I was to call these out maybe as little a and little b, right, as familiar values of little a and little b, and actually come up here and maybe say, let's make little a that -5, the lowest we can be in the domain, and let's let +5 be the upper bound that we want to look at or examine in all of our items. And now I can come along and call that a. This was also going to be a b maybe, or if we wanted to, we could play around with that, make a couple more tables and Bezier curves and more arrows, and have several arrows illustrating our path throughout here. But let's just go with the 1 throughout the entire path. And then where else did we have -5s and 5s? Down here. So let's call that A. Let's call that B. And I think that is it. The behavior should be the same, but what's nice about this is I can now come along and say something like, well, what was our other example? If we go back to our other example, right? Here's our other example. 3 sine t, 3 cosine t. I can now put that into r bar of t, decide on my bounds on the interval, that's 0 to 2 pi in this problem, change that up in a and b, and I don't have to rewrite the whole program. It will run with that respectively. All right? I may have to tweak a few things here and there, but it was not going to be a whole rewrite situation. So what do we had there? Let me go ahead and bring the Mathematica back over. All right? We had as this was what? 3 sine of t, and this was 3 cosine t. All right? And we're running this from 0 around to the value of 2 pi, right? And if I hit enter, it gives me that illustration there, folks. And can I make this arrow larger? Let's go large. No, that's not going to work for us. I think I have to adjust the arrowhead size. I'm not going to get into all that here. We can always make our visualization a little bigger if we want to. Right, that might help also. And here's our arrowhead. Our arrowhead's up there. The green might be some of our problems. So let me get rid of that. There we can see our arrowhead a little clearer. And if this is from 0 to 2 pi, we can certainly see this is our orientation around that curve. What's the issue here? Notice how we're incrementing. Maybe that's a third variable we put in. Maybe we put in there Oh, this is the problem. It's incrementing by 1 each time, which isn't necessarily a nice increment around this graph. Let's get something a little more consistent there. Let's actually make that upper bound a variable value. Maybe we make that, we could call it C if we wanted to. We might say here del T1. So del is delta. Delta stands for change in. So we go del T1. Let's make that change by a pi divided by 8. Right? That'll be nice. Let's see if that gives us a good looking picture here. Yeah, see that that plots out our points along that curve a little bit more succinctly, right? And just remember that is that change in delta. And if you're ever looking to put in a little of documentation, this is the change in table 1 values, right? And that just holds onto that as some documentation. It's surrounding your text with some stars and parentheses. And you can use more than one star if you need to, just to highlight something or to make a layer of information or whatnot in your documentation. But we're going to say this is the upper bound on parameter. We could call this the lower bound on parameter. Right? That just hangs out in that documentation. And unfortunately, I didn't set declare that, so it's repeating each and every time. Right? Yeah, that's kind of nice. We can come over and see, well, what about some other function, right? Maybe we have t squared plus 2t, and maybe this is, let's go with, just maybe e to the t. Right? That's the exponential function. Or you could even, I think exp also is exponential, but I know e to the t will also work here. And let's just go from 0 to 1. No real domain concerns. And let's have this all increment by tenths. Right? We get that curve there. Right? We do get this curve seen down here in our illustration, folks. Right? So this is a Mathematica program, folks. This is now a nice little compact program that you can use to do two-dimensional vector analysis. At least be able to start to look at its values graphically. One other thing I might add here is you might be interested in, well, where am I at my lower bound? And there is a way to actually call that out too here. Let's make one more list plot. Let's call this plot 2. And let's have it call out R bar of A. Let's see what happens. Well, first of all, let's just make sure that this will graph for us. So that's that point right there. Let's, one way to call it out is by size and color. So we can maybe call that out with purple, and maybe we make it a little bigger than all the rest. All right, and let's actually, oh, I see what's going on there. I do need to wrap this in some parentheses. The list plot, or braces, the list plot needs its points in a set of braces, right? This list plot, the table's output actually spits out a set of braces around the braced items, right? If we were to go back and look at table 1, you can see it puts a grand braces around all the other braced items, right? All the other setted up items. If we're not using the table to call out the list plot, we do need to use, in the list plot, we do need to use braces around what we're calling out. Now, and then I'm going to come down here and drop this into plot 2. And there it is, right? There we are at time t equal to a. So you can, let me draw this down close enough so you can see it. There we are at time t equal to a. So that's one way to call it out. Another way is actually you can also use what's called this is a little bit more tricky, is you can use what's called the call out command. This is where t equals a. And you can see there it highlights in our graph where t equals a, and it actually points to it. And you can call out anything. I can call out graphs. I can call out points along this curve, right, and so forth. I can also put that into a specific position. I can maybe go to the right, and it'll position it out to the right. You can call out values, or since we're in two-dimensional space, I can actually use some coordinate to call that location. And it looks like maybe 0.5 comma 0.25 maybe. 0.5 comma, and I just see I switched off my screen. Hold on here. Back to the screen. 0.5.25. Got to remember not to hit that control pad on the right too much, because it does control my system here, my OBS, my broadcasting software too. So let's see if that changes things around a little bit in our picture. Oh, I lost it now. Where did it go? 0.5, call out. Why aren't you appearing now? Oh, is it my scaling? Okay, I think it is the scaling along this axis. Mathematica does do this at times. It does truncate our graphs. One of the things we can do to help avoid truncating our graph. P0 is our plot commands. Plot range. You could call it out as full. Right? That'll show the whole picture where everything will fit in. Automatic. I think that gives us something similar here, but it doesn't get us quite down to the 0 comma automatic. Let's make the upper bound automatic. There we go. Now that's a little nicer picture, and you can actually see what happened there when I was doing my call out. I was calling out too low because things were truncated. I might call out a little higher here this time, 0.75 and maybe 0.25, right? So maybe we call out at 0.2, don't do it again, 5 and 0.75. Might be a little cleaner on a call out. So that is our location where t equals the value of a. Right? So that's another way just to start to highlight some different aspects of your analysis here, folks. But we are 40 minutes into this demonstration. I will come back and maybe do another quick one with, well, I could probably just show you that real quick here. If we were to do a curve, for instance, a parametric curve, we want to plot this out in 3 dimensions. Parametric plot 3D is what we would use. Right? Let's see here. I just want to make sure I get this right. Right. We're just going to need the 3-dimensional vector and our description of the parameter. So I think back here in this description here our third case was a description seen there, right? Let me bring that over into just quick view. So we were looking at, oh, I lost it in this illustration. We were looking at this function here 3-dimensionally, right? So let's consider this case back in Mathematica. And let me scroll Mathematica up so you can see what I'm doing down here. But I am making a parametric plot 3D here. And it is going to go in as a 3-dimensional vector. Here we had, I think it was 2 comma cosine t comma sine t, right? Where we're going to look at values of t here, maybe from, they don't really tell us. We could do any domain value. Let's look at one cycle. We're dealing with sine and cosines, and we know those cycle over a cycle from 0 to 2 pi. And there, we get an illustration that looks a bit like this. right? A couple of plot commands here. To get a little cleaner picture, we might do box ratios is the command here, and we put that in as a set 1, 1, 1. We'll make that more of a standardized picture, right? Where all the dimensions of the box are the same, but the labeling along the box, the scaling is inconsistent. Take note, right? Let's shrink down the image size a little bit. Yeah, that's maybe just a little, tweak it a little more. There we go, right? Notice in Mathematica, you can grab the graph, and I'm just left clicking on it and spinning it around. I can left click on it and hold the control and zoom in and out, or I can left click on it and hold the shift and pan it left and right in the window, right? So there's a lot of manipulation tools that you can use in Mathematica to kind of explore your graph, folks. And all this is available in the cloud options. If I want to label my axes, it is just axis label. And we're going to want maybe, again, X, Y, and I'll be brief here because I'm trying to be brief, and Z. Right. And all the plot styles also work. If you did a plot style, if you want to do more than one of them, you got to do directive, and this is how you change color and size and other things along those lines, opacity. So maybe I want to make the plot red, right? And I want to change its thickness, right? And you can call out words. We can make it thin. Oh, maybe that doesn't work. So I want to be careful there. Let me not head down that route. So we're trying to be brief. But if I have more than one plot style that will work, I can put those in the directive command. But there, I get a nice little illustration there of that. I can play with the ticks. The ticks are the things called along the edges in both graphs. If you make a three-dimensional shape, you can play with the mesh, grid lines. You can start to research some of the different plot options. You can also make tables in 3 dimensions, and you could approach what we did above also down here 3-dimensionally with just a parametric plot as your base plotting. I do think these are, you'll have to seek out how to do plots in 3-dimensional space. List plots, I think is list plot 3D. Yeah, it is list plot 3D. And we'd have to make that on some table. So maybe I'll call out like table 4. And let's call table 4 values of R of T. Well, I can't do that here. I didn't call out R of T, did I? So here I'm going to go ahead and just grab that whole thing, copy and paste it over into here. And call that out for values of T from 0 to 2. So you can see the problem of not writing up a program, having to adjust this each and every time. It didn't do what I quite expected with that list plot. I think it's list point plot. It is. List point plot 3D. That's my problem. And you got to have a capital D. Right? There, put those plots out in space. And I could actually make this a plot 1 in this case. Well, I don't want to get into the other ones. So let's call this maybe plot 9. I know I didn't have table 4 and plot 9. And let's call this plot 10. And again, I'm going to do show. I want plot 10 to be the base plot. And then everything's built on top of that, layered on top of that. Right? We can do that with the show command here also, folks. Really interesting stuff using this Mathematica and building these programs here, folks. This is maybe the first program that you're kind of introducing yourself to here in Mathematica. And it's not too heavy. It's not too heavy, and it does build upon some fundamental ideas, right? Fundamental ideas that happen in Mathematica and happen in mathematics, right? And yeah, if you're have a programming mindset, it's not too hard to figure out how to program in this system. Vector valued function analysis, folks. Quick little demo on those functions. I kind of wanted to turn it into that because otherwise it's just me pointing at these pictures on screens, and I think you benefit a little bit more from hopefully what I just given you. And it doesn't have to be this tough. Like I said, you can just parametric plot it in two-dimensional space, or you can just parametric plot it three-dimensionally, and you can get a really rough graph. But if you want to add some of those detail elements, like I have done here in this program, certainly I showed you how to do some of that. All right. And how to get some output here, how to get some interesting output. But with that said, it's late. It's late. If I told you what time it is, I don't know. It's 12:30 a.m. on a very early Monday morning. My hope was to have this out sooner. I can't sleep. So, I got some other things done. I wanted to do this. Felt like talking for a while. Felt like doing a Mathematica demo. It's been a while since I've worked in here, so I'm going to shut up so I can get this uploaded. You're going to see this uploading. Hopefully you caught this uploading, and if not, it probably won't be till the morning that I get it posted. And I know this is not useful to you whatsoever when you're watching it now, but just talking to myself. It's late at night. All right. Have a good one, folks. See you in class tomorrow.